here? We did the top.
We did both of these before, but I just wanted to use this as a recap. What a Michael donor and a Michael acceptor are. We're talking about from the point of view of electrons. So Michael donor is going to be a nucleophile. So it's going to be a doubly stabilized enolate. Or a Gilman reagent works as well.
Those are the donors.
So
Then
I guess we've done these are two different reactions, right? This is not considered a Michael.
Well, you said Michael donors are nucleophiles, doubly stabilized enolates.
Yes. So these are your examples. I guess it is donor, but Gilman reagents are also considered Michael donors, but because they're going to give you that the Michael reaction is going to preferentially give you that 1,4 addition. So we're going to break a pi bond, but we're going to add our nucleophile on the beta carbon relative to the carbonyl. Versus the more reactive molecules, more reactive nucleophiles will add a carbonyl carbon instead. Right, so that's why this gets classified as a separate reaction. Is because these are the reactions that put the addition on the beta carbon instead. And remember that these were we call these Gilman reagents. They react just like Grignard reagents, except they're a little bit less reactive. Just the bottom, the one with the copper lithium. So with them being less reactive, that just means that we're more likely to get either a partial reduction of a carboxylic acid. So if we had R1 carboxylic acid plus, I shouldn't do it like that. R2, we'll call it R prime, just to indicate that's a different R group. CuLi, that'll reduce it to a carbonyl, not take it all the way to a tertiary alcohol. So that would give us R prime. Right, so that's the other place we've seen these Gilman reagents. The way they work here is it's going to allow us to put our new R group, our nucleophile, going to attack on that beta carbon. So just to recap, I know we've already done these, but just to recap, for A, what that's going to look like is our Michael acceptor, which is our alpha beta unsaturated carbonyl. We're going to break that pi bond and add our ethyl group right there. We can't use a Grignard reagent for this because a Grignard reagent would add right here and potentially would add here as well. So Grignard reagents are too reactive for this situation. It gives good yields, but not necessarily enough control. There's a few cases where even the enolate is going to be too reactive, so we need something that's even less reactive than the enolates. So we can't just use. So if it's not a doubly stabilized enolate, we can't just go through this process. And so we need a different synthesis if it's a singly stabilized enolate, we can't just use the Michael reaction. So first what we do is we convert the carbonyl into a less reactive nucleophile, an enamine. Right, so I think we talked about enamines back when we talked about carbonyls, right? These enamines are just when we have a nitrogen with an R group attached to an alkene, enamine. And so with these being even less reactive than the enolates, this means that we can have an enamine react and add in the beta position. So if we had an enamine react, it's really going to be, this is going to be the reactive resonance structure, right? This is the one that looks like an enolate. An enolate reacting with the alpha beta unsaturated carbonyl, we get the beta carbon or the alpha carbon reacting with the beta carbon. So what would this say if we use cyclohexanone? Is going to be our, sorry, not cyclohexanone. We use the enamine. We converted this to an enamine first. So we'd have something that looks like.
It's still under like our Michael, yeah.
This is, yeah, it's basically a subset of Michael reactions. We're getting into subsets of subsets now, right? We had that react with the same alpha beta unsaturated carbonyl. It's going to react, move that way. So after first step, we'd have something that looks like let's see how I can draw and leave myself enough room. And then if we add a little mild acid workup, we're just going to protonate that negative charge. If we're under acidic conditions, yes, because it has a lone pair that can be protonated pretty easily. If we put it under neutral conditions, we're just going to pull one of the hydrogens off of the nitrogen. So initially, get this. So the alpha carbon from one molecule attacks the beta carbon from the other. And then if we neutralize the acid, we just deprotonate this and we wind up with that's an imine, right? Which we know how to convert this back to being a carbonyl, back from our carbonyl chapter, right? We talked a lot about imines and enamines and converting them back and forth. So I believe we would just have, actually, if we did the H3O plus, it would, instead of neutralizing it to get to be neutral, if we expose this to H3O plus, it's just going to hydrolyze this back to being a carbonyl. Right, that was the other way, that was the reaction. It's this.
We just like erased it through like 5 days.
Yes.
We might right.
Oh, come on, can you keep up anymore? No, sorry about that. I did make that a little sloppy. I think I have it written more neatly on the next couple of slides. So the way we would do this, first things first, convert it to an enamine. And remember for it to work, to make the enamine in this form, we had to use the secondary amine. Alright, we heat it. So we can try and remove that water. Use the evaporation of water as part of our way to drive this forward. Then we do a micro addition of our enamine. So a micro addition would be more descriptive way. We didn't want to use just the neat reaction. We call it a 1,4 addition to an alpha beta unsaturated carbon. Obviously, that's a little bit more mouthful.
To the enamine you just created.
Right, so the enamine we just created is going to be the Michael donor because it's going to have this resonance structure that looks like an enolate. And our Michael acceptor is our alpha beta unsaturated carbonate.
And then we wind up, if we have this nitrogen with that's positively charged with a double bond here. We know that that's not super stable. In fact, that's one of the reasons why we need an enamine instead of an imine in the first place. So it's not actually going to stay this way very long. As soon as we expose it to the acid, it's going to convert back. So just the same way that if we said 8 always means a deprotonated form of something, right? Enolate, carboxylate, etc. Anytime you add an EO, means it's the extra protonated version of it. So for instance, NH3 is ammonia versus NH4 plus is ammonium. Same with like water and hydronium. Protonated form gets that EM suffix. So an imine that's big, that's got a positive charge, it's called an iminium. It's the positive charge, so more than the protonation in this case, but that's what that suffix means. I also realized I was reading a paper on pedagogy and teaching reading to elementary school kids last week. And I realized I talked a lot about suffixes and prefixes. Did you learn how to break down words by suffixes and prefixes? Okay, so you're in part of that. They're going back to that approach when it comes to teaching reading, as opposed to you were probably taught using, they call it just reading for context. If you don't know a word, guess it based on the rest of the sentence, which is valuable, but maybe in my opinion, not as valuable as being able to look at a word and say, well, I know what that part means.
Yeah.
So sorry, I've been talking over your head with that this whole time, but that's how I was taught to when I see an unfamiliar word. So hopefully you've picked up a little bit of that. I'll have
Yeah.
to say it more explicitly in the future.
No, I get it in this class for sure.
All right. So let's do practice. Stork enamine synthesis. Stork is actually somebody's name. It's not, has nothing to do with the bird. Got an alpha carbon. We know if that's an alpha carbon, this is from either direction, it's a beta carbon, right? But if we're talking about adding a beta carbon reacting with an alpha carbon from the other side, those are going to be our two pieces that we're trying to fit together here.
You have to do a site there. Right?
So that will be, if we want the beta carbon on one side to react with the alpha carbon on the other side. The piece, the red one, that has the beta carbon reacting, has to have been reacting from this molecule. Right, because there's our beta carbon that's going to be doing our reacting. And on the blue side, we want to take this molecule and turn it into something that'll react in the beta position. So we can't just use LDA like we would normally use to make an irreversible enolate, because that's going to make one that's too reactive. It'll react with the carbonyl carbon on the other side. So this is when we want to use enamine synthesis, is when we have just a singly stabilized alpha carbon. So instead of just using LDA, we're going to use any secondary amine under acidic conditions. And that's going to convert it to our enamine. Right, if we're writing exactly away from the last slide, we can say minus H12 here. And making the enamine is valuable because this molecule looks a lot like an enol, but it's slightly less reactive. So this one has a resonance structure that looks like that iminium.
When did I have to-
So with the two R groups on, yeah. Oh, sorry. Change the colors. One carbon, two are.
Well, now we got all our carbons where we want them to get to our final product, right? So what's the last step? Proton transfer. And a quick hydrolysis of the iminium. So we just expose it to H3O plus. Don't forget your carbon stuff. Yeah. Yeah. Taylor, are you okay if I clear this site? So when we have an enamine, enamines look like this, right? So if this is what our molecule looks like, the resonance structure is going to look like. Remember, anytime we get a lone pair next to conjugated with a pi bond, you basically have this lone pair move into the sp2 orbital or into the p orbital here, and that's going to push these electrons over. So once you do that, your resonance structure is going to look like a double bond between the nitrogen and the sp2 carbon. And you move and you push the pair of electrons over. And this looks just like when when we had an enol, we did the same thing with an enol. It also has a very similar resonance structure.
Yeah. It's what I did, I just realized nitrogen positive.
Anytime you got a nitrogen with 4 bonds, it's going to be positive. So I left off here because it's sharing more than it normally wants to based on the periodic table. All right, how do we feel about that? It's just one more reaction to put on there.
Yeah.
Under the subcategory of Michael reactions. Right, which is also already a subcategory of a nucleophile attacks pi bond. Well then, congratulations. That's the end of the chapter on alpha carbon chemistry. And the last new material we're going to cover this year. You did it.
Taylor's still writing things down. She hasn't even had a second to fast. I'm fasting.
How do you fast by studying?
Okay, so we got a couple more assignments. I'm gonna give you your practice test later this afternoon.
Okay.
I'll put it up and that'll be your last homework assignment. It's Tuesday, got a week.
We still have class Thursday.
We do, but you had a chance to look at the practice test so we could use it as questions.
Right, but what to staff, are we doing our, I think we should take exam Tuesday and Friday or Tuesday and morning.
I will,
Well, we have all of Thursdays. No, are we done with it? Well, but you don't wanna like overdo your brain right before. Okay. If you want, we can do Tuesday and Friday. Sean's stuff really likes.
I'm here either way. And you don't have to agree on it, Riley, if you wanna do it Tuesday morning. Tuesday morning? Okay,
We have to assess the schedule, like, so I had it by student.
okay,
And I was. Should we practice with the one is finishing up my presentation. Very ready last night, so I have